Okay, yeah, thank you very much, Tangying. Thanks for the opportunity to tell you about this work and to speak in this, to speak in this nice event. So, I'd like to tell you about this work on quantum algorithms for dissipative nonlinear differential equations, and this is joint work with Jin-Peng Liu, who I think actually maybe is here in the session, and Herman Kolden, Nuno Loureiro, Krovi, and Konstantina Trivisa. So they're my collaborators on this work. And if you're interested in reading more about it, I mean, of course, I won't be able to get into, there are many details that I'll have to sort of skip today. But if you want to sort of hear more about it, there's a link here to a paper on the archive that gives a lot more detail. Okay, so just as a little bit of background, as you're probably aware, the idea of quantum computation is that if we, store and process information on quantum mechanical devices using quantum mechanical states, there are some problems we can solve a lot faster than we can using ordinary classical computers. And, there are some examples of problems for which we get exponential speed up, or at least we think we get exponential speed up, including problems like factoring, but, also some other things. And there are, many more problems for which we think we get, polynomial speed up, or in some cases for which we really can prove that we get polynomial speed up. Now for a much wider variety of problems. And the area of quantum algorithms really tries to understand, what are the kinds of problems for which we can get speed up, and what are the amounts of speed up that we can get for these various problems. But what I want to talk about in this talk is sort of another direction, aside from the problems that I've mentioned, in these examples above, which is to give quantum algorithms for problems in numerical analysis, and specifically for differential equations, although I'll talk about a connection to, linear systems as well. So the idea of these algorithms, which really hope to be of the kind where you can get exponential speed up, is to really represent the sort of vector in some kind of linear algebraic representation of a problem. So there's some vector that describes the solution, and you're going to represent that by a quantum state. So a state x, a vector x in some n-dimensional complex vector space, you can think of as corresponding to a quantum state ket x, which is just the normalized version of this vector, just the L2 normalized version of this vector, but now using only log n qubits, right? So if this is an n-dimensional state, of course, you only need like the log of n qubits to represent that vector as a quantum state. Now, of course, such a state is not the same thing as having an explicit description of the vector, but it's some kind of encoding of that vector. And in principle, for depending on the problem, it may be possible to prepare that state using a number of operations that scales only polynomially in the number of qubits. In other words, only polynomially in the log of n, which is much less than the amount of time that it would take even to just to say what that vector is, just to write out that vector explicitly. So you could, in a very fast way, imagine producing this very succinct encoding of a vector in a high-dimensional vector space. So as I said, this is a quantum encoding of the solution. It's not the same thing as having a full explicit description of the solution. So it's not something you can compare in sort of like an apples to apples basis with, like, let's say, producing the entire vector, in MATLAB or something, in some representation where you have, the entire vector written out. But on the other hand, you could potentially do it much faster, and it might still be useful for some kinds of problems because it, that vector somehow, summarizes some aspects of the solution, and maybe it provides useful information, for some problems. Okay, so the sort of tool that we're going to use to be able to get at this kind of, to be able to produce this kind of encoding of a solution is quantum simulation, the idea of simulating quantum mechanics on quantum computers. And this was like, the original motivation for quantum computers going back to, for example, Feynman in the early 1980s. He and others realized that if you want to simulate quantum mechanics, then a very natural way to do that is to build a quantum mechanical system that has exactly the right kinds of degrees of freedom to represent and simulate quantum states. Whereas this is something that we think is hard on classical computers in general. So in this quantum simulation problem, we're given some Hamiltonian that describes the dynamics of a quantum system. We have some time we would like to evolve for. We're given a copy of the initial state, and we would like to produce the final state that we get by evolving with this Hamiltonian under the Schrodinger equation for that time. And it's okay maybe to do that approximately, so up to some error epsilon. And for this problem, like a classical computer classical computer cannot even represent the state efficiently. To explicitly write out the vector, would take an exponential amount of space in the number of qubits that this Hamiltonian acts on. And on the other hand, a quantum computer can potentially produce this state. Now, just as I was describing when we were talking about this as an approach to linear algebra, that's not the same thing as having a full description of the state, but it's kind of exactly what you would need to be able to, predict the outcomes of quantum mechanical experiments on a system that was in that state. And in particular, you can use that representation to answer questions that apparently are hard for a classical computer to answer. So this is a very kind of fundamental problem in quantum computing, and I think it's a very natural target for sort of getting quantum mechanical speedups for solving interesting problems. The most sort of obvious thing that you might do with such a quantum simulator would be to simulate physics, right? To simulate quantum physics. So for any kind of physical system where quantum mechanics plays a significant role, like in quantum chemistry or maybe in condensed matter physics or in high energy physics, you could simulate the dynamics of such a quantum mechanical system efficiently using this kind of quantum simulation algorithm, and you could predict exactly the kinds of things that you would be able to learn from an actual experiment, measure observables on the final quantum state. And this would potentially be a very useful tool for doing computational physics. But there's another way to sort of think about using quantum simulation, which is not necessarily to use it to simulate like realistic physical systems, but to use it as a tool for implementing other kinds of quantum algorithms. So you may have heard about the idea of adiabatic optimization, where we encode the solution of some problem in the ground state of some Hamiltonian, and we try to get into that ground state by adiabatically evolving from some other Hamiltonian with a known ground state. There are also algorithms based on quantum analogs of random walks, including an algorithm for evaluating Boolean formulas. These are all examples of algorithms that use Hamiltonian dynamics to solve some computational problem that's not about some physical system, but it's just a kind of a computational problem that's stated in some abstract way, but that it's useful to think about using Hamiltonian dynamics to solve. And so what I'm going to talk about today is an example of this sort of idea of applying quantum simulation to high-dimensional linear algebra problems, and this has become sort of I guess whole subfield of quantum algorithms, where we try to understand how we can use this kind of high-dimensional linear algebra that we can implement using quantum simulation to solve problems about linear systems of linear equations or systems of differential equations. And today we're going to talk specifically about nonlinear differential equations. Okay, so let me explain a little bit about this quantum linear systems algorithm that was first proposed by Harrow, Hasidim, and Lloyd, that shows how you can connect quantum simulation to high-dimensional linear algebra. So this is really kind of like the workhorse of many of these algorithms for solving differential equations and for other kinds of high-dimensional linear algebra tasks. So the kind of problem that we're interested in is that we've got some system of linear equations. Let's say we have n equations in n unknowns, and we have some kind of description of the matrix A and the right-hand side vector B, and our goal is to find a solution X to the system of equations AX equals B. And so, let's imagine that this matrix A is invertible, and then the solution, then there is a solution, and then that solution is given by A inverse times B, right? So that's the thing that we would like to try to learn. Now, of course, if we want to do this, we want to produce an explicit description of X, this solution X, then that's going to take time linear in the number of equations and the number of variables, because just to write out what the solution is would take that amount of time. So, that would be the best you could hope for, would be a linear time algorithm if you have to write this thing out explicitly. But now what we're going to do is we're going to think about this model where we allow ourselves to just produce a quantum encoding of the solution. And then, maybe we should think separately about how exactly to use such a thing. But that's going to be our goal, to produce a quantum state proportional to X that encodes X in a quantum mechanical way. So we're going to do that. We're going to imagine that our goal is to produce a state ket X that's proportional to A inverse B. So it's the normalized state proportional to A inverse B. And to be able to do that efficiently, we're going to have to make some other assumptions. We're going to assume also that we can prepare a quantum state ket B that's proportional to the right-hand side B of this system of equations. So we're going to prepare that as a quantum state in the memory of our quantum computer. And also, we need the system of equations to be somehow nice. So one sufficient condition would be that it's sparse, and that we've got some black box that sort of reveals where the non-zero entries are. So specifically, we should be able to ask for any row or any column of A, where are the non-zero entries? There should be not too many of them, like only poly log n such non-zero entries. We should be able to find out where they are and what the values are in those entries of the matrix A. That's actually not maybe the most general condition. There's this more general framework of block encodings, for example, that a block encoded A would be also good enough. But to make things really concrete, you can imagine that maybe we have a system of sparse that the matrix is given in this sparse representation. So we have some sparse system of equations. Okay, so what Harrow, Hasidim, and Lloyd showed in 2009 was that you can actually solve this task. You can prepare this state, ket x, in polynomial time, specifically time polynomial in the number of qubits, so polynomial in the log of the number of equations and variables in the system, and also polynomial in 1 over epsilon, so here where you produce the state with error at most epsilon, and also polynomial in some measure of the distance from singularity of the matrix as measured by the condition number. So the condition number is like the product of the spectral norm and the spectral norm of the inverse of the matrix. This is like the ratio of the largest to the smallest, singular value of the matrix. So this is like telling you something about, so if the matrix is singular, so that this x isn't even well defined, then this condition number is infinite. And if this condition number is really big, it kind of means the matrix is close to singular, and so the problem should be hard. And so indeed, the complexity of this algorithm, will grow with kappa. And specifically, I think for this original algorithm, the complexity went like the square of kappa. So, this talk is not going to get into sort of full technical details of algorithms, but just to give you kind of a general idea of how the algorithm works and how it's related to quantum simulation, what it's going to do is it's going to think about performing a quantum simulation of A, thought of as like the Hamiltonian of a quantum mechanical system. If it's not Hermitian, you can sort of think about a closely related matrix that is Hermitian that will do the same job. And then what you can do is you can use the quantum phase estimation algorithm to estimate the eigenvalues of A, in superposition. In general, if you're in a state that's a superposition of different eigenstates, then you can estimate the eigenvalues in coherent superposition. But then the basic idea is to replace each eigenvalue of A by its inverse. And so if you replace lambda by 1 over lambda, that's effectively inverting the matrix. And so, because A and A inverse is not necessarily a unitary transformation, you can't do this deterministically, but you can do it using post-selection, and you can show that the overhead of doing this is not too great, provided the condition number is not too large. Okay, so that's the idea of this original algorithm, and then there's been a bunch of subsequent work that's improved the performance of this algorithm, and sort of the best algorithms now have complexity that's actually linear in kappa. This is thanks to an improvement due to Andres Sambinas using this idea of what's called variable time amplitude amplification. And there are also algorithms that have complexity that's, not only linear in kappa, but also polynomial in the log of 1 over epsilon, and not just polynomial in 1 over epsilon. Coming from these ideas related to what's called the linear combination of unitaries framework. Okay, so these improvements are not going to be all that crucial to the algorithms that we're going to talk about today, but the sort of main message I want to give is that we now have a pretty good understanding of the quantum complexity of solving this task of preparing this quantum state ket x that encodes the solution of a large system of linear equations. Okay, so now what we would like to do is we would like to think about how we can use this to solve differential equations. And just to sort of, as a little bit of a warm-up, the main point of today's talk is going to be to talk about nonlinear differential equations. But as a warm-up, let's think about the case of linear differential equations. Okay, so imagine that we're given a system of linear ordinary differential equations. So, let's imagine, to keep things simple, that it's a first-order system. If it's a higher-order system, with higher derivatives with respect to t, you could always introduce variables to rewrite it in this way. So let's say it looks like dx dt equals some matrix A, some square matrix A, acting on x plus some inhomogeneity B. And then you're given some initial condition x of 0, and so this is like an initial value problem. And then you want to determine the solution x of t at some later time, capital T. Okay, so this is actually just a generalization of Hamiltonian simulation, right? Because Hamiltonian simulation is the problem where this is the Schrodinger equation. So that's like where A is an anti-Hermitian matrix, right? A is like minus I times the Hamiltonian, and where also the system is homogeneous. So there's no, B equals 0. So that's we know we can do that because that's quantum simulation. But actually, we can handle this much more general situation where we have a kind of a fairly general system of linear differential equations using this quantum linear systems algorithm as a subroutine. And this idea of using this approach to produce this kind of quantum encoding of the solution of a system of linear differential equations was first suggested by Dominic Berry in a paper in 2014. So the main idea of this algorithm, which is going to be sort of carried through for much of the stuff that we're going to talk about today, is first of all to relate the system of differential equations to a system of linear equations. So you can imagine using something like the finite difference method, where you sort of discretize in time, and this can give you a system of just a system of linear equations that, if you discretize finely enough, will be a good approximation of the system of differential equations, just by considering kind of finite differences. And then once you have that linear system, it's just a matter of sort of analyzing the complexity and the error, right? Analyzing sort of what is the computational cost to produce a solution that will give you what you want to within some controlled error. And so you have to bound the error of approximation, both from the errors introduced by this finite difference method and the errors that are inherent to the quantum linear systems algorithm. You have to understand, how does the condition number of this system of linear equations relate to properties of the system of differential equations. You have to understand how likely is the procedure to succeed, because again, these algorithms involve post-selection, so you have to make sure that they're succeeding with sufficiently high probability. But you can basically understand all of these things sort of in terms of the properties of the original system of differential equations, and then you have a pretty good understanding of the performance of this quantum differential equation algorithm. So of course, I've emphasized this several times, but these caveats are important, so I'll emphasize again that this approach is going to come with the same kind of caveats as the original quantum linear systems algorithm, namely that we need to have a sufficient implicit description of the system. So we need something like, for example, a sparse matrix representation of A, the ability to prepare a quantum state proportional to the vector B, etc. And also, we will only produce a quantum encoding of the solution. We will not produce an explicit description of the solution. So this is, you have to figure out how to make use of such a quantum encoding. But at the same time, you're doing something much faster than you would have any hope of doing with a classical algorithm. So the hope is that that's going to be useful for some applications. Okay, one particular issue that arises here, which I'm not going to sort of explain this in full detail, but I do definitely want to mention it, which is that one of the things that you will find when you analyze the performance of the algorithm as a function of sort of properties of the system of differential equations is that for the algorithm to be efficient, it's very important that the solution not decay exponentially. Right. So in general, when you have a system of differential equations, you can have terms that are decaying. And if you have sort of a state whose overall norm is decaying exponentially, then the ability to sort of produce a quantum state proportional to that state, which sort of has decayed away to something exponentially small, but you produce a normalized state proportional to that state, that's basically post-selection on an exponentially small amplitude. And that's something that's very computationally hard to do. Like if you could do that in general, then you could solve what are called PP hard problems. So this is even harder than NP hard problems. So that's something that we don't expect to be able to do. So we don't expect to have efficient algorithms for such cases. And so that means that this algorithm can only hope to be efficient for a certain class of sort of nice differential equations that don't have such overall exponential decay of the solution. Okay. And we'll see a similar kind of restriction when we talk about nonlinear differential equations as well. So this original idea was proposed in this very nice paper of Dominic in 2014, but there's been a lot of follow-up work that has sort of generalized the class of equations that can be considered and has also gotten shown better performance. with variations on the algorithm, considered things like time-dependent coefficients. What happens when you have a boundary value problem instead of an initial value problem? What happens in the setting of partial differential equations where you have derivatives with respect to space? Various kinds of things. I mean, I'm not trying to cite all the papers here, but there's a lot of work that's been done in this direction. Okay, so the main thing that I want to talk about, in the talk today is, what can we say about the setting of nonlinear differential equations, right? So far we've been talking about, systems of linear equations, systems of linear differential equations, but, what about nonlinear differential equations? And obviously, nonlinear dynamics are sort of, arise in many applications. It would be great if we could, have an efficient way of using quantum computers to understand nonlinear dynamics, because that would surely have lots of applications if we could handle a really general class of nonlinear dynamics. So actually, it's kind of so clear that this is an important thing to think about. This was actually like the very first thing that was done, even before this work of Dominic Berry on the special case of linear differential equations. Actually, like maybe just like in a month or two after this paper of Harrow, Hasidim, and Lloyd was posted, there was another paper by Layton and Osborne where they proposed an algorithm for a quantum algorithm for nonlinear differential equations. And what they sort of hoped to do was to get the same kind of good scaling with dimension that we see in the Harrow, Hasidim, and Lloyd algorithm for systems of linear equations, namely that we try to produce this quantum encoding of the solution for an n-dimensional system with complexity that's only polynomial in the log of n. And they actually showed how to do this already in this 2008 paper. They showed that you could get complexity that's polynomial in the log of n. But the problem with their sort of approach is that if you want to sort of handle an ordinary differential equation that you want to evolve for time t, then the complexity of their approach will actually be exponential in t. So that means that in practice, you can't sort of consider dynamics that run for very long because the cost is exponential as a function of that time. So this was, sort of a nice sort of like first step in this direction, but this is a pretty serious roadblock. Until just this past year or so, it was kind of not known how to improve on this to get complexity that's any better than this exponential in t scaling. So the main idea of this Layton and Osborne approach was, essentially that the way one can imagine realizing these nonlinear terms is by having multiple copies of the solution, right? And this is a kind of a fairly standard trick for sort of introducing a nonlinearity to sort of like linearize a system of equations by having multiple copies of the solution, right? So if you sort of think about the having multiple copies of the solution, then a term which looks like a nonlinear term as a function of one copy could actually be a linear term in multiple copies. Like if you want a quadratic nonlinearity, you can do that with only two copies of the solution. So that's a way of dealing with the nonlinearities. But there's a problem with this, which is that you do have to do this post-selection, in their approach, similarly to the for the reason that you have to do it in the HHL algorithm, namely that you're trying to do something that's not necessarily unitary. And so these copies will be used up as you run the algorithm, as you try to evolve the quantum state. So you need to have many copies, but because of the quantum no cloning theorem, you really need to maintain those copies throughout the entire algorithm. You can't sort of like run your algorithm for a while, and then when you realize you need more copies of the solution, you just copy it, right? Because that's not something you can do in quantum mechanics. You can't clone an unknown quantum state. And this is the source of this exponential in time overhead, having to have this, basically you will need to have an exponentially large number of copies of the solution around initially, even if you only care about a quadratic nonlinearity, because you'll be sort of using up these copies at an exponential rate as you try to evolve. So that's a problem, and it sort of seemed like kind of a fundamental obstacle. And in fact, you might think that it's really kind of a completely fundamental obstacle because nonlinear dynamics, in general, are just going to be hard to simulate, right? Nonlinear dynamics are computationally powerful. It's known, for example, that in a variety of models of nonlinear quantum mechanics, so if you take sort of quantum mechanics and modify it by introducing some nonlinearities to the dynamics, almost any way that you try to do that, you end up with a model that can solve hard problems quickly. Like, for example, you can solve the unstructured search problem, in polynomial time, which you shouldn't be able to do with quantum computers. Like, you could solve it in time polynomial and log n, where n is the number of items that you're trying to search through. So that suggests that certainly you shouldn't be able to handle general nonlinear dynamics, and so maybe this is really kind of like a fundamental barrier. Okay, so that's where things sort of stood, until we kind of started thinking about this problem, and so I want to tell you about how we sort of, because of these no-go results, certainly we're not going to kind of completely crack open nonlinear dynamics and have a quantum algorithm that's going to work for nonlinear dynamics in general. But what we did was to sort of identify a class of nonlinear dynamics that we can handle, and where you can say something interesting about algorithms that don't have this exponential overhead. Okay, so here's this slide is maybe more complicated than it should be, but I wanted to give you sort of like the precise description of the problem that we handle. So we consider specifically the case of quadratic nonlinearities. You can imagine having higher degree nonlinearities that you encode either in a similar way or by reducing to this form. But just to keep things simple, let's imagine we have quadratic nonlinearities. And actually, the way that that's written here in this sort of description of what the nonlinear differential equation is specifically in terms of having two copies of the solution, right? So you can encode this quadratic nonlinearity through some linear operator acting on two copies of the solution. So here we have an inhomogeneity f naught of t that can be some time varying inhomogeneity. The linear term and the quadratic term, for our purposes, we're going to imagine are not time dependent. They're time independent. One could think about trying to generalize this, but this is specifically what we did. We consider these to be time independent. And so F1 here is like an n by n matrix. F2 takes, maps these sort of like n squared degrees of freedom in the two copies down to n degrees of freedom. And that tells you sort of incrementally how the state evolves. That gives you du dt. And if you solve this differential equation, for time, for some time capital T, like that's the goal, right? To produce a quantum state u of t that you would get by evolving this differential equation for time capital T. And so, we're going to assume basically that we have the kind of implicit representation of the differential equation that we have in the linear case. We've got sort of oracles that allow us to prepare all the relevant things describing these matrices. And now the question is, under what conditions can you solve this problem efficiently? And sort of the main, new thing here is that we're gonna sort of characterize the problem in terms of this parameter that we call capital R. And so R is some kind of measure of like how nonlinear the system of differential equations is. So specifically, here in the denominator is the sort of, so we're going to assume, let me just back up. So we're going to assume that the linear part of the dynamics, so that's this matrix F1, has negative eigenvalues, and they're ordered in this way so that like lambda 1 is the least negative, the eigenvalue with the least negative real part. Right, so it's the real parts of these eigenvalues should be negative, so that there's no exponential growth. There's sort of only dissipation, and lambda 1, or rather the real part of lambda 1, captures somehow how much dissipation there is. Right, everything is promised to dissipate at a rate at least by this magnitude of the real part of lambda 1. So this sort of measures the dissipation in this system of differential equations. And the norm of F2 is some kind of measure of the strength of the nonlinearity. The norm of F0 is like measuring the strength of this forcing term, right? There's this, possibly time-dependent forcing term in the equation. So if the equation is strongly dissipative, then somehow this will be fairly large relative to these terms, and R will be small. And if it's strongly nonlinear or really strongly forced, then R will be large, right? That's what will happen if F2 and or F0 are large compared to this quantity, which is measuring the scale of the dissipation. Right. And so, what we've done is sort of to identify this as a parameter of interest. And what we're going to show is that actually we can solve this problem provided, R is, the value of R is good, right? And we'll see what is a sort of suitable value of R kind of momentarily. Okay, so you can think about R, as I just said, as sort of quantifying the strength of the nonlinearity and the driving relative to dissipation. And it's somehow, it's not exactly the same thing as the Reynolds number, but it's like kind of qualitatively, related in some way to the the Reynolds number. In if we're talking about a system of equations that's describing fluid flow. Okay. Okay, so here's the kind of first main result. So we have two kind of main results. One is kind of a positive result for these systems of differential equations. The other is kind of a negative result or a hardness result. So the algorithmic result is as follows. So it says that if R is not too big, so specifically if R is less than 1, then there's a quantum algorithm for this problem that I described on the previous slide that's efficient, right? So it's going to have a query and gate complexity that's like quadratic, or well, times log factors, but basically quadratic in the amount of time that you want to evolve for. So this is much better than the exponential scaling of this Layton and Osborne result. And it's polynomial in the log of n. So n here is the number of equations, right? The dimension of the system. So that's good. We have this, polylog scaling in the dimension. In other words, polynomial in the number of qubits that it takes to represent the solution as a quantum state. And it also scales with the error basically like 1/epsilon times some logarithmic corrections. And it also, so this is why I mentioned before this kind of issue about the scaling with the sort of the possibility of exponential decay of the solution. It also scales linearly in Q, where Q is like basically how much the solution, it measures how much the solution can decay. So it's like the ratio of the initial norm of the solution to the solution after it's evolved for time t. So if the solution decays exponentially, which can happen in some cases, if the solution decays exponentially, then that's going to be sort of an exponential contribution to the complexity, which is not good. But if you're in a situation, which can also happen, if you're in a situation where the solution does not entirely decay away exponentially, then it's possible for this to be really a polynomial running time. Okay, so I'm not going to sort of describe in full detail how the algorithm works, but let me just say what sort of some of the main ingredients are. So we use a kind of approach to linearizing the system of differential equations that's known as Kalman linearization. This is sort of an old idea in sort of numerical methods for differential equations, but we give a novel convergence analysis that allows us to understand the performance as a function of this parameter R, and to show that things work efficiently, provided R is less than 1. And I'll say a little bit more about this on the next slide. And then once we've done this linearization, so that we have a system of linear, so this Kalman linearization procedure basically takes this system of nonlinear differential equations and relates it to a larger system of linear differential equations. So now once we have the system of linear differential equations, then we can do kind of the standard thing of trying to handle those linear differential equations, with these quantum techniques. So we can discretize, in time to get a system of just regular linear equations. And then, we basically just have to try to apply the quantum linear systems algorithm on those, which involves figuring out how to prepare the relevant quantum states given the sort of state preparation procedure we have for the original differential equation. And then we just have to analyze sort of the performance of that, of the algorithm in terms of like the condition number of the linear system and the sort of success probability of the procedure for preparing the solution as a quantum state. So that's kind of like a very high level overview of some of the things that go into the algorithm. But let me on the next slide just talk a little bit more about this Kalman linearization procedure, because this is maybe sort of the most interesting and maybe most novel part of this kind of algorithmic result. Okay, so the idea of Kalman linearization is to approximate the nonlinear ordinary differential equation, or the system of nonlinear ordinary differential equations, by an infinite sequence of linear ordinary differential equations in sort of many copies of the state. So it's going to be a system of equations in U, but also 2 copies of U, 3 copies of U, etc. So here, when I write U tensor K, I mean U tensor U, etc. With K copies of U. Okay, and to sort of explain how this works, let's look at a very simple case where we just have a scalar equation, right? So instead of having this sort of like vector case, let's imagine that we just have a scalar. Then instead of having to write tensor products, I can just write like powers, right? Okay, so then here a quadratic differential equation looks like this. So du dt is like au squared plus bu plus c. So now what we can do is we can say, let's imagine that u squared is like a variable in its own right. We're going to introduce that as a new variable in the linear system. If you do that, then this looks like it's now a linear equation if you think of u squared as like a separate independent variable from u. Of course, the issue with doing that is now you need to know what are the dynamics of u squared. So you need an equation for how u squared evolves in time. But you can do that just using calculus, right? So now what is the time derivative of u squared? Well, you just use like the chain rule, and you can rewrite it like this. And if you just plug in this expression for du dt and you expand out, you get this expression for the time derivative of u squared, right? And you can continue to do this as many times as you like. Of course, you'll never be done because you'll always, at each step, you'll be introducing a new variable. Like now here you have u cubed, right? So now you need to know what is d by dt of u cubed, et cetera. But you can do this sort of for a while until you get tired and you decide to stop, and then you can just truncate. And then if you take this truncated system, if you truncate at a high enough level, you can sort of hope that that's going to give you a good approximation to the underlying, like truly nonlinear dynamics. So now you've introduced many new variables, but you can also hope that you don't have to introduce that many more variables before you get a good approximation. Okay, so if you try to do this in general, in sort of like the matrix case, you get something that looks like this. So the sort of like time derivative of these variables, yj, which are basically sort of like standing in for j copies of the solution, looks like this kind of block tridiagonal matrix acting on the vector of y's with some inhomogeneous term. And then the things that appear in the blocks are basically like, they involve these matrices, f0, f1, and f2 that encode the original nonlinear differential equation. They're like in this, kind of vector version of this. This is like f0, this is f1, and this is f2. And so that's kind of what things look like in the more general case. And so now what you have to do is you have to understand, like, what can you say about how large this capital N has to be, this truncation, before this gives you a good approximation. And what you can show is that really like a fairly low order is sufficient. That this capital N only has to scale actually logarithmically in the evolution time, and like logarithmically in the inverse error, and it also scales only logarithmically with like the the norm of f2 describing the sort of scale of the nonlinearity. Okay, so that's like this truncation theorem that we use to do the analysis. Okay, so that's some kind of high-level description of some of the algorithmic ideas, and I'm happy to take more questions about it, if you have them. But what I'd like to do next is sort of move on and talk a little bit about the sort of flip side of this, which is a kind of hardness result that tells us something about what happens when R is bigger. So remember that this algorithm, maybe I'll just back up. This algorithm, only is going to be efficient if R is less than 1, if the problem is not too strongly nonlinear. In other words, if there's sort of sufficient dissipation relative to the nonlinearity and the driving. But what happens if R is bigger than 1, right? That's, it'd be nice if we had an algorithm for larger values of R. Could we hope to have an algorithm that would work under the same kind of conditions for, R equals 2, R equals 10? What could we possibly hope for? And so what we're able to show is that actually, we can't hope even for an algorithm with this level of generality, even for R equals 2. And in fact, even a little bit less than that wouldn't be possible. So we know that there are these results about the hardness of simulating nonlinear quantum mechanics. Now, what we're looking at here is a situation where we have dissipation, right? So in nonlinear quantum mechanics, there's no dissipation. Like the state always remains normalized. The dynamics are like norm preserving. They're not linear, but so I guess it doesn't make sense to say they're unitary, but they're norm preserving. So there's not dissipation. So the sort of the hardness results that we know from before for nonlinear quantum mechanics, we can't exactly use. But what we are able to show is something like that, even in a situation with dissipation, provided there's not too much dissipation, right? We know if there's enough dissipation, then actually this puts us in this R less than 1 regime where we can actually handle things with the algorithm that I just described. But what we show is that if R is bigger than the square root of 2, then already we're in the regime where we can't hope for an algorithm because these dynamics could be used to solve hard computational problems. So we show that if if r is bigger than square root of 2, then we can come up with some instance of this general quantum quadratic ordinary differential equation problem that I introduced, that will have to have complexity that's exponential in the evolution time. And so let me just say kind of very briefly what the idea is. It's similar to how the hardness results work for these models of nonlinear quantum mechanics. It relates to the hardness of distinguishing non-orthogonal quantum states. Right. So if we have two quantum states that are, they make some, maybe they're close to each other, but they're not exactly the same state. So they're vectors in Hilbert space that have kind of a small angle with respect to each other. Well, those are states that are going to be really hard to distinguish, right? You can't distinguish non-orthogonal states in general. And if the states are really similar, it should be really hard to distinguish them. But on the other hand, if you have nonlinear dynamics, then you can have states that are sort of initially close to each other, but the angle between them can increase under the dynamics, right? I mean, that can't happen with unitary dynamics, like that preserves inner products. But if you have nonlinear dynamics, then it can potentially push apart these initially hard to distinguish quantum states. And so what you can do is you can construct a quadratic ordinary differential equation that will rapidly distinguish non-orthogonal states. And then what that means is that if you could solve this, this quantum quadratic ODE problem, with these initially hard to distinguish states, it would allow you to push apart those states and thereby distinguish them. And that's something you shouldn't be able to do. So it means that this problem actually has to have high complexity. That's the kind of general idea of this argument. So yeah, I mean, this kind of comes from two places. One is just the hardness of distinguishing quantum states. This is actually a pretty standard thing. So maybe I won't sort of like explain this in full detail. I mean, basically, like if you have quantum states that have some inner product close to 1, in other words, the states are close to each other, then you should need a lot of copies of those states to distinguish them. And in particular, you can show that if the overlap is like 1 minus epsilon, then you need a number of copies of the states, or you need an amount of time, using a procedure that has the ability to prepare these states that scales like 1 over epsilon. And you can show this by just kind of like very standard kind of quantum information arguments. On the other hand, as I said, you could come up with nonlinear dynamics, and truly you can do this with dissipative nonlinear dynamics that allow you to distinguish, these non-orthogonal states. So, I mean, here specifically is how we do this. So let's just consider this like very simple quadratic ODE. This is just the scalar equation. So du dt is minus u plus r times u squared, right? So this r here is really exactly the parameter r that we talked about before, because it's the ratio of the quadratic term. So here there's no forcing term. So it's just the ratio of the quadratic term to the strength of the dissipation. And here the strength of the dissipation is just 1. Right, because it's dissipative because there's a minus sign here, and the magnitude of the coefficient describing the dissipation is just 1. Right, so the ratio of the nonlinearity to the dissipation is capital R. Right, that's this capital R parameter that we had before. And the solution of this equation, okay, it's a nonlinear equation, so in general it's hard to solve nonlinear equations, but this one you can solve. It goes like this. This is just the exact solution of this particular nonlinear differential equation. And you see that in particular, there's this kind of like, exponential decay, right? So there's this e to the t term that appears in the denominator as a function of the evolution time t. And so what we're going to do is we're going to think about what happens if this thing acts on the two basis states of a qubit. So if we have a qubit that starts out in a plus state, so in the uniform superposition of 0 and 1, then that state will not evolve. Or, I mean, it depends maybe exactly what the parameters are, but certainly up to normalization, it doesn't evolve, because we're going to have the same dynamics act on both basis states, and they're initially both, they both have amplitude 1 over the square root of 2. Right? So certainly up to normalization, this state is not going to evolve if we let its two components evolve in the same way, under the same dynamics. It's going to remain proportional to the plus state. But on the other hand, if we sort of tip a slight amount away from that state, so we rotate away by an angle, theta, from 1 over root 2, 1 over root 2, then that state will change exponentially in t because of this, exponentially changing term in this solution of this differential equation. And so just to show kind of what's happening in some concrete case, here's what happens if we take r to be the square root of 2 and theta to be 0.01. So we rotate away by an angle like 0.01. from pi over 4. And then you see what happens is that one of the terms, like I forget which is which, but maybe this is the coefficient of 0 and this is the coefficient of 1. Well, it's either that or the other way. But one of them is going to be sort of increasing exponentially, and the other one is going to be decreasing exponentially. I think this figure is maybe I forget if this is after the state has been normalized, but it sort of doesn't matter. The picture will look approximately the same whether it's before or after the normalization has been applied. So one of these coefficients is going to be growing, the other one is going to be decaying, and so after you evolve for some not very large amount of time, you see that the state will be very distinguishable from the original plus state. And so this problem of distinguishing the plus state from this state, which has to be very hard if theta is very small, actually is something that you can do quickly if you can simulate these dynamics. And so what that means is that actually simulating these dynamics must be hard. So and so what this is just sort of a picture of what happens with these particular parameters, but what you can show in general is that the time that it takes to separate states that have initial overlap 1 minus epsilon, if you want to separate them to where they're sort of distinguishable with constant probability, where they have constant, where their overlap has sort of become has decreased by a constant amount, we'll scale like the log of 1 over epsilon, because really these amplitudes are diverging exponentially. Right? And so since we shouldn't be able to take exponentially close states and distinguish them after only a polynomial amount of time, it means that really the cost of doing this really has to scale exponentially in the amount of time that we try to evolve. Okay, so those are sort of our two main results, and sort of in the last part of the talk, I just want to talk a little bit about some kind of potential applications of these of these ideas, and I want to sort of mention some kind of numerical thing that's maybe a little bit interesting about something to possibly investigate in the future. Okay, so you can imagine trying to apply this algorithm kind of in any problem where nonlinearities play a significant role. And one such place that's maybe relevant to our sort of lives at present is in sort of epidemiology, right? So if you want to sort of model the sort of population dynamics in a pandemic, you can do that with a system of nonlinear differential equations. And so here's one particular model that people have used to model the dynamics of populations in a pandemic. And this is not something that we came up with. This is like a model that occurs like in the epidemiology literature. And so in this particular model, I mean, the details are not so important, but there's 4 parts of the population. There's the susceptible part, the part that's been exposed, the part that's been infected, and then the part that I guess has been infected but then has recovered. And there's a bunch of parameters in the model that sort of capture various features, like there's some set of individuals that's coming into the population that's captured by this influx parameter. There's a rate at which the population is being vaccinated, etc. And if you sort of like look at the in the literature, places where this kind of model has been used to study the dynamics of actual pandemics. So this is a paper published very recently about the COVID-19 pandemic. If you sort of look at realistic parameters and then maybe assume that the vaccination happens a little bit faster than it sort of actually is happening in practice, but you sort of consider parameters that you could consider as sort of not totally unreasonable, then you can be in a regime where this parameter r is less than 1. So I'm mentioning this to say that this assumption that the dynamics are nonlinear but somehow only weakly nonlinear, something like that can arise in a realistic situation. And now, of course, this system of equations that's written here, there's only 4 variables. So like, there's not really much advantage from going to a quantum computer and taking advantage of the ability to handle really high dimensional systems efficiently. But you could imagine cases where maybe you have, a large number of interacting cities, and maybe you have a much larger number of variables that capture these different parts of the population in these different cities, and people move between the cities, et cetera. You could imagine doing something like this, to sort of model such a situation. So I don't want to sort of claim that this is going to, quantum computers are going to be the thing that's going to sort of save us from, pandemics like COVID-19. But I just want to sort of connect this a little bit to, something that maybe a situation that we're sort of encountering now, and where you could imagine that these kinds of ideas could potentially be useful. The other potential application that I want to briefly mention is relates to fluid dynamics. So obviously we have the sort of Navier-Stokes equations that describe fluid flow, and which are hard equations to solve in general because they're nonlinear. We looked at sort of a special, sort of a simplification of one of those kinds of models, something that's called the forced viscous Burgers equation, to see a little bit about how the Kalman linearization would perform, for that model. And I just want to sort of show this this plot where we looked at the behavior of the Kalman linearization procedure. So now, just obviously like studying it classically, we're not putting the algorithm on a quantum computer, but we're just looking classically at how well the linearization method performs. And what we see in this experiment is that it actually performs surprisingly well for this particular nonlinear model, even in a regime where R is much bigger than 1. So of course our our algorithmic result only says that things, only guarantees that things will perform well if R is small. Our hardness result only says that in the worst case things have to perform badly if R is big. And both of those things allow for the possibility that the algorithm could actually perform well in some special cases, even when the nonlinearity is stronger. And so that's exactly what we find in this particular model. So I think this is kind of intriguing because I think it suggests that exactly the kind of algorithm that we considered could potentially perform well, beyond the regime where we currently know how to show that it behaves well. So I think it's a nice kind of question for future investigation to think about, how can we identify cases where something like this happens? What are the classes of equations where actually we can handle stronger nonlinearities with this algorithm and still have it behave efficiently? Okay, so let me now try to wrap up. So just to sort of summarize some of the things that I've talked about. So we've shown that there's an efficient quantum algorithm that will allow us to produce this quantum encoding of a high-dimensional system of nonlinear differential equations, under suitable conditions, right? So we don't expect to be able to do this efficiently in general, but we can do it if the nonlinearity and the forcing are sufficiently weak relative to dissipation, or in other words, if the system is sufficiently strongly dissipative. And there's also this condition that the solution has to not decay exponentially. So we know that this is a problem that includes things that are hard for classical computers. Like this general class of problems is certainly includes BQP hard problems. So this is doing something that we think is really showing quantum computational power. This requirement that the solution not decay exponentially is somehow necessary. Like this is just a condition that we know we need to have for the algorithm to be efficient because of the hardness of simulating post-selection. And we also know that sorry. I mean, let me just back up. So I just mentioned these items to sort of say that in some sense this algorithm is it's really doing something that we think is hard for classical computers, and it has this dependence on this parameter that characterizes the decay of the solution that we don't think we can improve significantly. Also, we don't think we can significantly improve the dependence on this parameter R, because of the hardness result that we prove. And I want to mention just briefly that if you don't consider a driving term, right? So if you consider homogeneous differential equations, then actually because the system is dissipative, the things will necessarily decay exponentially for long times. So you can't have an algorithm that's going to be efficient, for long time evolution. But if you consider the possibility of having a driven system of differential equations, then they don't have to decay exponentially, even despite the fact that they have to be dissipative. So we really can, consider a regime in which the algorithm would be efficient. Okay, we also have this kind of hardness result that says that we can't hope for an algorithm that's going to be efficient for general nonlinear differential equations with strong nonlinearities. But at the same time, I mentioned this numerical evidence that shows that the algorithm may actually be efficient in some cases, even if R is bigger. And I think that that's an interesting thing to try to investigate. So this is my last slide. So I think there's a bunch of, interesting questions to think about for the future. We left open this window kind of between R equals 1 and R equals the square root of 2, where actually we haven't characterized, the sort of efficiency or hardness of the problem. It would be nice to kind of close that window, although I would say that's maybe more of a sort of a technical thing than a sort of really practically important thing. um, our algorithm has complexity that's quadratic in T, and I don't think we can expect to have performance better than linear in T, but it would be interesting to see kind of where things should lie between linear and quadratic. Another kind of related question is about the dependence on epsilon. So some of these algorithms for high dimensional linear algebra problems have complexity polylog 1 over epsilon, whereas here we have complexity that goes basically like 1 over epsilon. So it'd be interesting to know, is this kind of much better performance something that one can potentially achieve? And then, so this is the question that I just mentioned on the other slide. I think it would be nice to identify classes of equations for which we can handle these larger values of R. We have numerical evidence that maybe that would be possible. And I think it would be great to get a better understanding of that. And finally, I've really, sort of described an algorithmic tool that you can use to prepare some quantum state, that encodes some information about the solution. But this is not the same thing as saying exactly how you would use a quantum computer to solve some interesting problem having to do with nonlinear differential equations. So if you really want to use this kind of algorithm to solve some problem of interest, you have to figure out, like, how would you realize this model where you are able to characterize the system of equations succinctly? How would you make use of the final quantum state to learn something interesting about the problem? And I think it would be great to think more, think in more detail about how to really use these algorithms in practice. Okay, so thanks very much. I'll stop there, and I'm happy to take questions if there's time.